Integration by parts is what we use when we end up with an integral that we cannot integrate using either an algebraic rearrangement or substitution. And what we want to do is use a formula where we have the original integral, so original integral here, and we use the formula to get a different rearrangement, and that different rearrangement looks like that. And what that rearrangement does is gives us a new integral, which hopefully is better than the original integral. So that new integral on the right-hand side, we want that to be an easier integral, or one that we can actually anti-differentiate. So the key to this is we need to select different parts. So we need to select a u part. Okay, we need to select a dv part. And then we need to generate the du and the v parts. So we're going to generate a du by differentiating, and we're going to generate the v part from the dv part by integration. And the way we choose these parts is that we always choose a dv that is the hardest that we are able to integrate. So in this case here, we don't have, we can't actually integrate any of this. So the part that we can only part we can integrate is a dx part. So that's going to be the dv part in our formula. Okay, so that's original dv here. And we then integrate that to generate the v part. The u part then represents the other part of that expression. So there's a u part here in the formula, and there's a u part in the expression. So we have u, and we differentiate this to generate the dv part, sorry, the du part. Okay, so once we select the parts and generate the other parts, we now have a formula. So our new integral, our original integral was log x dx. Our new integral is going to look like this. So using the formula, we end up with uv. So I'm just going to start with x is my v, u is my log function. And then minus, we end up with this new integral part. And this is the part that's of interest to us, because if this new part is integratable or anti-differentiable, that the formula has served its purpose. So this part ends up being v du. Okay, so we need to select the v part, or put our v part in. So in this case, it's x. And the du part, we're going to replace with dx over x. Now this cancels out, and our new integral, we can integrate. So our new integral looks like this: x log x minus the integral of dx. So the integral of log x ends up being x log x minus x, and then don't forget the plus c since it's an indefinite integral. Well, sorry, it's not an indefinite. So we then, once we establish that, we want to put our bounds in. Okay, so I should keep my bounds in this part here, and the bounds we're going to plug in. So plugging this in, we get 5 log 5 minus 5 minus 2 log 2 minus 2. So this ends up being log 5 to the 5 over 2 squared. When I combine those logs, 5 minus negative 2 is negative 3. So that's the area under that curve from 2 to 5. So again, we're using that formula. We're just starting with an original integral that we can't integrate, and we're generating a new integral using parts. And hopefully we can integrate that new integral. So in example E, we need to use integration by parts as well. So we need to choose our parts. So we're going to choose our u part, and we're going to generate a du, and we're going to select a dv part, and we're going to integrate to generate v. So the dv part is the hardest, more complicated part that we can integrate. So we're going to select cos x here. Okay, and then different or integrating this, we get sine x. The u part then ends up being just the x part, and then du we generate by differentiation. So the new integral that we're going to generate is going to be uv, so x sine x minus, and this is the new part, from 0 to pi over 2. It's going to be, since we started with u dv, we're going to use v dx, sorry, v du. So v is my sine function, and then the du just is a dx function. So at this point, we have generated the new integral, and the new integral happens to be anti-differentiable, so then this formula worked. So we end up with minus negative cos, so we end up with plus cos x, and then put in our bounds of 0 to 2 pi. Working this out, we end up with sine of pi over 2 is going to be 1, so we end up with pi times 1. The cosine of pi over 2 is 0, and then minus 0 times sine 0 is 0. Cosine of 0 is 1. So the area under that curve works out to be pi over 2 minus 1 units squared.